Okay, let's start. Hi, everyone. Welcome to Fall 2020 ML Seminar Series at UT Austin. It's my great pleasure to introduce Hamad Hassani from the University of Pennsylvania. Hamad received his PhD in 2014 from EPFL. After that, he spent 2 years at ETH as a postdoc. And then he was a research fellow at Simons Institute for a year. And since 2017, he has been an assistant professor in the Electrical and Systems Engineering Department of University of Pennsylvania. Hamad has received several awards, including Information Theory Society Best Dissertation Award, ISIT Best Paper Award, Air Force Young Investigator Award, and NSF Career Award. Hamad has worked on several different topics, including coding theory, submodularity, distributed learning, and very recently on adversarial training and robust learning. And today he's going to talk about some of his recent works on adversarial training and robust learning. And in particular, he's going to talk about two facets of learning robust models, fundamental limits and generalization to natural out of distribution inputs. With that, I hand it over to Hamad.
Right. Okay, let me just minimize this window. All right. Thanks, Aryan, for the introduction and invitation, and thanks everyone for attending this virtual talk. So the talk will be about learning robust models. And I'd like to begin with saying a few words about some of the main applications where robust models are important for. And these are safety critical applications. And here by safety critical, I mean any application where the detections, recommendations, or decisions impact the well-being of humans. A canonical example of this setting would be self-driving cars, where let's say the detection of pedestrians in a sidewalk would dramatically impact the safety of those pedestrians. Another application could be robotics, where the interaction between robots and humans is subject to obvious safety constraints. And also in medical imaging, nowadays, learning-based models are used to detect certain patterns that could lead to suggestion of treatments for different patients. And also, since the safety of patients are involved, this is also an important safety critical application. So the main message here is that machine learning models, when used and deployed in safety critical applications, must be robust and trustworthy. And talking about robust models, perhaps a natural starting point would be to talk about adversarial examples, given how this field is growing with this respect to the area of machine learning. So let me first explain what adversarial examples are all about. So assume that you train a standard classifier, let's say a neural net classifier, using some standard data set, let's say CIFAR, ImageNet, MNIST, whatever. So you train this model using this data, and at test time, we know that the performance of the model on newly unseen images or newly unseen data points that come from the same domain that the training data comes from, the performance is quite good, meaning that if you use your model to classify, let's say, an image of a panda with high probability and high confidence, the model would classify it as a panda. However, the phenomenon of adversarial examples is as follows. So let's take the same image and let's add to it a very small amount of noise. Of course, the choice of the noise is adversarial, meaning that you choose the noise according to the data point and the model that you're working with adversarially. And the perturbed image, so the image on the right, for us as humans is really indistinguishable. However, the perturbed image would be classified incorrectly by our model. So for example, in this case, would be classified as a given. Let me now dig in a bit more into the mathematical properties or the mathematical picture that we have about adversarial examples. Typically, in machine learning, data points are treated as points inside some Euclidean space, RD, where D could be as large as the number of pixels inside the image. And assume that around each data point, we draw a ball of radius epsilon. And think of epsilon to be a very small number. Now, within this ball, we are looking for points, perturbations of the original image, such that these perturbed images would be classified incorrectly by our model. And these are called adversarial examples. Of course, as I said, the choice of the perturbation should be well crafted with respect to the model that we are using and with respect to the data point. However, the main message here is that adding small amounts of noise can cause misclassification. In other words, modern learning-based models, such as deep neural networks, are highly fragile with respect to these small norm-bounded perturbations. And this is well documented within the area of machine learning. There are now thousands of papers to analyze different properties of adversarial examples, as well as provide robust training algorithms to basically make our models robust against these type of small norm-bounded perturbations. And given the fact that these adversarial examples are important sources for misclassifications in our modern learning-based models, a natural question that arises here is what other types of transformations can cause misclassification? It turns out that there are quite a few of such transformations. So in addition to the small norm-bounded perturbations that I mentioned, we can consider spatial transformations, for example, rescaling or rotation. So if you take your image and you choose an adversarial angle to rotate the image, the rotated version of the image might be misclassified. So with high probability, it will be misclassified by your model when the angle is chosen adversarially. Out of distribution data is when you train in one domain and test in some completely different domain. Adversarial patches is another type of transformation. Sensing mechanisms, it turns out that the quality and the type of the data acquisition device also matters. So for example, if you capture your images with one camera and test with a different type of camera, this would be subject to some misclassification error according to this study that was done a few years back. And finally, I'd like to say a few words about a very broad class of transformations, which I call natural variation. And these are transformations that are caused by working in natural or dynamic environments. Since the second part of the talk will be about natural variation, I want to say a few words about this class of transformation. So the central question that I want to answer now is, how does data vary in natural environments? And in order to illustrate this, I will be considering a very simple data set, a very standard data set of street signs from different scenes. So for example, there is a car. So these pictures are taken during, let's say, sunlight, during a sunny day, during daylight, on different street signs, I think inside the city of Atlanta or some specific city. So the classification task is to basically classify the street sign that's inside the image. That's a fairly standard machine learning task. You can basically train a neural net using your training data. And now let's assume that you train this neural net on this data set, and you want to deploy this neural net in real world, meaning that, for example, you have a self-driving car, you want to use the neural net to classify street signs on newly captured images that you see in real world. Now, when working in natural environments, nature doesn't really give us exactly the same thing that we expect. Doesn't give us the exact natural conditions that we expect, for example, daylight or basically sunny weather. In fact, the nature could add different types of natural variation to our image. So this image that you see on the right, the snowy version, somehow corresponds to the image to the left, right? So they are semantically the same. They have the same street sign in them. They are about the same street view. However, they differ in the level of natural variation. And in the same manner, the nature could add other types of natural variation. For example, rains, or dirty camera lenses, darkness, fogginess, blurriness, grayscale, exposure, and a variety of other natural transformations could be considered here. So this very broad class of transformations is called the class of natural variation. And a natural question that arises here, given the fact that neural nets are highly fragile with respect to those small norm-bounded perturbations, is whether or not neural nets or modern learning-based models are fragile with respect to these type of transformations. Now, in the next slide, I want to answer this question using basically some experimental results, very simple experimental results that are done on natural variation. So let's consider the same data set that I mentioned in the previous slide. So these are street signs taken during daylight in sunny weather. And your neural net is trained using these type of images. And at test time, I would basically try to classify the street sign on images that have different levels and different types of natural variation. So the curve at the top, which has very high accuracy, corresponds to data that comes from exactly the same domain, meaning that you capture newly unseen images that are taken during daylight and sunny weather. Okay, so this is just the success of deep learning. If your test data is the same as your training data, then with high probability and high confidence, you get good results, you get good accuracies. And as expected here, you get around 90% of accuracy. Now let's add a bit of natural variation to our image. So let's assume that you take those images in a snowy day where there is some light snow. So you see that the performance drops by a few percent. Now let's add a bit of more snow and the performance drops more significantly, around 20%. And if our images are captured during a snowstorm, then there would be a huge drop in the performance by around 30% or so. So the point here is that neural nets or deep learning models are also highly fragile with respect to these type of transformations.
So just to
and arguably,
sorry to interrupt. There was no snow in the
training. No snow in training.
Okay.
Right. Very good.
And this snow is added with an artificial process?
So in this data set, I think, yes, the snow was added in the artificial process, but I mean, later on in the second part, I'll talk about different data sets that you can think about other types of natural challenges like darkness or different lighting conditions. And those in those data sets or in those environments, things are natural.
And there's no systematic misclassification. It's just you're just showing us the accuracy. It's not like
right.
Okay.
Right. Good point. All right. So arguably, these type of natural transformations are more relevant or more important for our safety critical applications compared to small norm-bounded adversarial examples. So my point here is that the same type of effort that's been done, that's been put on studying adversarial examples should somehow be put to study these kind of important class of natural variations. So in this talk, I'll consider both classes of transformations, adversarial examples and natural variation. The first part of the talk will be about adversarial examples or norm-bounded perturbations. In the case of norm-bounded perturbations, we have a precise understanding of how mathematically these adversarial examples are defined. Okay, so there is a ball around each data point, and within that ball, we are looking for a worst-case example. So given this mathematical understanding, we can design robust training algorithms. And as I said, there has been an area that's grown out of these observation of adversarial examples within the field of machine learning. However, it's really fair to say that our understanding about adversarial examples is still at its infancy. We don't really understand much. I mean, there are a variety of interesting and surprising phenomena which we observe and we cannot justify or interpret. And also the performance of our robust training algorithms is not satisfactory compared to what's expected. So the first part of the talk will be about fundamental limits, different trade-offs between different types of accuracy, robust accuracy, standard accuracy that we get in a foundational problem of learning called regression. And also towards the end of the talk, I'll also mention a bit about classification too. So that was the first part. The second part will be about natural variation. In the case of natural variation, the situation is very different. For natural variation, we don't even mathematically understand natural variation. We don't have models that would basically mathematically model the impact of natural variation. And also, since we don't have good models, we don't really have good and consistent algorithms to robustly train our learning-based models. So the second part of the talk will basically do a paradigm shift from adversarial examples to natural variation, and we'll introduce a framework called model-based robust learning, which tries to address these two challenges. So first part of the talk, we'll consider mostly theoretical trade-offs, curves, and so on. Second part will be about this framework of model-based robust learning, and also we will evaluate the framework using a variety of experiments and data sets. All right, so let me proceed with the first part of the talk, which is about adversarial examples. And this is a joint work with Adel Javamard and Mahdi Sultan al-Kotabi from USC. And the paper was published very recently in the Conference of Learning Theory. Okay, so let me continue with developing this mathematical framework of adversarial examples. In order to do so, I'd like to take a step back, like basically go 50 years back and talk about the standard setting of supervised learning first. Okay, so we are going back 50 years, there's no adversarial examples, there's nothing like that. Only standard supervised learning. So in supervised learning, the basic assumption is that data comes from a distribution, D, which is oftentimes unknown. And our goal, our problem is to find a model, theta, that minimizes the expected loss. Here and throughout the talk, L would stand for the loss, and L of X, Y, and theta that you see on the right would basically measure the performance of our model theta on the data point X compared to the true label Y. Okay, so standard supervised learning would basically want to minimize the expected risk, and the expectation is taken to the original, with respect to the original distribution of the data. So however, we don't really have access to the true distribution of the data, and instead we have access to training data, and training data points that come IID from the same distribution. And hence, the common practice is to solve the empirical risk minimization problem, which basically replaces the expectation with empirical average over the data points. Okay, so this E at the top is replaced with the empirical average. And well, as I said, there is 50 or 60 years of research and progress made into the supervised learning framework. We now have very good models that work well on test data points that come from the same distribution as training data points. However, as I explained before, the solution of ERM typically fails badly on adversarial examples. So if you consider a ball around your point and you look at the worst case example within that ball, there is this fragility here. Now, the right formulation when you have adversarial examples is as follows. Data still comes from a distribution, so the distribution of the data doesn't change. However, at test time, you would get worst case examples within the ball. And this would give us the following minimax formulation. So let me focus on the inner maximization part. The inner maximization part just tells us that you should go over the ball, the epsilon ball, around each data point, each input X. And within that ball, you look for the point that maximizes the loss. And you want to find a model that has the best performance with respect to these worst case points within those balls. Okay, so that's the minimax formulation that we need to solve when we are doing adversarial learning. And well, this is typical. I mean, in robust optimization, robust statistics, whenever you have some element of robustness, you would typically encounter minimax problems. Again, as before, we don't know the true distribution of the data. Instead, we have training data. So one way to relax the minimax expected objective is to relax the expectation with the empirical loss. And this is just one way to do it. There are many other ways to relax the objective. So the robust ERM objective is just the empirical sum over the data points that we have, and inside we have the max objective. So here delta I would correspond to the worst case point inside the ball of data point, the ith data. Okay, so then you try to basically solve this robust ERM objective using different optimization methods. And let's use theta hat of epsilon as the solution of robust ERM. So whenever we have epsilon throughout the talk, this means that there is some adversarial component in it. Okay, so epsilon would basically correspond to the power of adversary. All right, so let me just summarize things a bit here. Supervised learning, we know that the solution of ERM works well on test data coming from the same distribution as the training data, but fails badly on adversarial examples. In order to improve robustness with respect to adversarial examples, we do robust ERM. That's one way to do it. And of course, theta hat of epsilon, the solution of robust ERM, definitely would work better on adversarial examples. However, it has been repeatedly observed that the performance of theta hat epsilon, the solution of robust ERM, would degrade on the original or benign data points. In other words, if you measure the performance of theta hat of epsilon on non-perturbed data points that come from the original distribution, the performance would degrade compared to the performance, compared to the solution of the ERM. So in other words, there seems to be a trade-off here. Let me show this trade-off using this two-dimensional plane, where on the y-axis I have the adversarial error, on the x-axis I have the standard error. So the performance of theta hat, the solution of ERM, would basically lie here. So the adversarial error is high. However, the standard error is very good. Standard error is low, but we know that it fails on adversarial examples, so adversarial error is high. The performance of theta hat of epsilon, however, is better in terms of the adversarial error. However, the performance degrades in terms of the standard error. In other words, it seems that we are paying a price to gain robustness in terms of the standard error. If we want to bring down the adversarial error, it seems that we need to increase, so the standard error would be increased. And this is what we observe algorithmically. So we want to understand what are the pros and cons of adversarial training with respect to these type of fundamental notions. So the key questions that we want to answer in this talk are the following. So first of all, what's the fundamental trade-off between robust and standard accuracies? Are these trade-offs that I just mentioned, are these algorithmically? Is it because of some of the shortcomings or some of the weaknesses that our algorithms have? In other words, can we find a model that has a very low standard error as well as a very low adversarial error? So these are fundamental trade-offs that we need to answer. That's the first question. Second question is, once we understand these fundamental trade-offs, no matter what the algorithm is or what the amount of data that we have available is, how can we algorithmically achieve those trade-offs? That's the next question. And finally, we need to see what's the effect of different properties of our, let's say, hypothesis class, let's say the size of the data, the model size, the effect of over-parameterization, and so on this trade-off. So we're going to answer the three questions in the context of Gaussian linear regression.
Hamad, I have a question.
Yes.
Yeah. So the trade-off you mentioned, does it come only during this framework, like when you are formulating the loss using robust ERM, only then, or like, let's say when I'm training a standard deep learning network, I will generally do rotation shifts and all that stuff in the beginning and basically augment my data to train the model, right? So
right.
I don't generally see it.
Very good question. So the fundamental trade-off, well, of course, you would fix the hypothesis class, let's say the class of neural nets, but the fundamental trade-off is independent of your whatever you do, of your computational power you do. Of course, you fix the hypothesis class. Okay, so there is no robust ERM objective. You directly work with the expectation over, let's say, the adverse. So expectation over the distribution of the data, and you want to characterize those fundamental trade-offs. Now, if you change your hypothesis class, let's say you are using a neural net, but you want to do some tweaks in the beginning and so on, then for the newly obtained hypothesis class, you might have a different type of trade-offs. But what we want to argue here is that these type of trade-offs, fundamental trade-offs, are quite general. Did I answer your question?
Yeah.
All right. Good. So these are the key questions that we want to address now in the setting of Gaussian linear regression. Let me briefly explain what this setting is. So here we assume that data x comes from the Gaussian distribution. I'm simplifying everything here. So the Gaussian distribution has IID components. Every component has unit variance, and the label would be generated by the inner product of the data point xi times the ground truth model, the true model theta 0, plus some additional noise wi, which is again generated according to Gaussian with variance sigma and everything is independent of each other. Okay, this is just a standard Gaussian linear regression problem. And of course, we assume that we have access to n data points that are generated IID from this distribution. So n labeled data points, basically, xi and yi. And the goal of linear regression typically is to estimate the ground truth, the basic model theta 0 from data. And in the adversarial setting, again, I'm simplifying everything, we will consider L2 adversarial perturbation. So we consider L2 balls around every input data point X. And here, epsilon test would be the power of adversarial test. So as I said, and this setting could be easily extended to general, more general covariance matrices and also other LP balls. But let me just simplify everything here and explain the results using this setting that you see here. All right, I need to also introduce a few other notions here. So given a choice of the parameter theta, so theta for you could be basically, these are the weights of your model. I mean, in general, they could be weights of your neural network and so on. So given a parameter theta, we would find the label, the predicted label by the model theta using this inner product that you see here. So the inner product of the input X and theta. And the loss that we are using here would be the quadratic loss. So we look at the difference between the true label Y and what's predicted by the model theta. The difference to the power 2 would be our quadratic loss. And there are two standard notions that we consider here. The standard risk, which is basically the expected loss of our model theta under the true distribution of data. This is called the standard risk. And there is the adversarial risk, which is the performance of our model theta under the worst case point inside this L2 ball around every data point X. Okay, so, and we want to understand how the standard risk behaves with respect to the adversarial risk. All right, so let's first talk about optimal trade-offs. So from now on, for the first result, I will assume that we have infinite amount of data available and we have infinite computational power. Okay, so I'm not talking about algorithms here. I'm only talking about optimal or fundamental trade-offs. And in order to characterize these optimal trade-offs, one way to think about it is as follows. So I go over all the possible models, all the possible thetas in RP. And for every model theta, I would basically put a point inside this two-dimensional plane, which the point is the pair standard risk and adversarial risk. Okay, so I'll go over all the possible values, p-dimensional models theta, and I would put all these points in this plane, and this would give me a region, right? And in order to understand these optimal trade-offs, I need to understand the boundary of this region. So for linear regression, this region turns out to be a convex region. So in order to understand the trade-offs, I need to understand what happens at the boundary of this region or at the Pareto optimal points of this region. So the points at the boundary have the following property. If you fix one of the coordinates and you try to decrease the other coordinate, the point will fall out of the region. So in other words, these points at the boundary are basically the optimal points. You cannot really do better than these points. And since for the regression problem, this region turns out to be a convex region, we can use a standard trick called the supporting hyperplane trick to basically characterize the boundary. So we go over all the possible supporting hyperplanes. This would be equivalent to trying to minimize the objective that you see at the bottom for different values of lambda. So basically, if you change lambda from 0 to infinity, it's like sweeping the boundary of this region. And by solving this problem, this minimization problem in terms of different values of lambda, you would basically characterize the boundary. So for the regression problem, it takes a few pages, but you can explicitly solve this minimization problem. So you can find theta of lambda explicitly, and you can basically draw the optimal, the Pareto optimal curve. So the details are not really important. What's important here is that there is a non-trivial trade-off happening here. In other words, if you want to for example, decrease the adversarial risk, you would have to increase the standard risk and vice versa. In other words, you cannot really find a model that has the optimal standard risk as well as the optimal adversarial risk. Okay, there's a non-trivial trade-off. And as I mentioned before, we are considering optimal trade-offs, meaning that we are assuming unlimited computational power and infinite data. Okay, so this is our fundamental limits, and it seems that there is a fundamental trade-off. So these two objectives, the adversarial error as well as the standard error, are somehow at conflict with each other, right? If you want to decrease one, you'll have to increase the other one, and this is just the optimal thing to do. Right, so these were the fundamental limits. The next question that we want to answer is how, or in using what algorithms can we basically achieve this optimal trade-off. So here I'll consider the robust ERM problem. So that's one way to relax. Remember, that's just one way to relax the original problem that was given as an expectation. And I want to study the solutions of the robust ERM problem. Okay, so theta hat of epsilon would be the solution of the robust ERM problem. And for us, for the linear regression problem, we are considering the quadratic laws and the robust ERM. So the inner sum that you see here would become just this simple sum that you see in red. Now, again, let me just remind you, the setting of linear regression, Gaussian regression was as follows. Data comes from the Gaussian distribution. The label is generated according to some ground truth plus some additional noise. Everything is independent of each other. And two important parameters that we will study later on would be the following: the sample size n, and the number of parameters of our model, the dimension of the model, which is p. And the regime that we want to study these trade-offs is the following. So we assume that the number of data points is large. However, the ratio between n and p, so the number of samples with respect to the number of parameters, this is typically called the over-parametrization ratio. This ratio is assumed to be fixed. So this is delta for us. From now on, delta would be this ratio. And we want to study trade-offs within this ratio. So it turns out, and this is the main theorem of the first part of the talk, that we can precisely compute both of these quantities, the standard risk as well as the adversarial risk, for theta hat of epsilon. This is given with this formula. So these parameters, alpha star, beta star, and tau star, these are just solutions of a simple, a very low dimension, a 5-dimensional problem. So all these parameters are scalar values. You can basically solve this low dimensional optimization problem, this 5-dimensional problem. You can solve it numerically. It's a convex concave problem. You can solve it numerically and find the exact values of these parameters, and you can plug those values into this formula to find the limits. Okay, so again, the details are not really important. In a few minutes, I'll explain the high-level picture of how to obtain these formulas. However, what's important here is that we can characterize precisely these algorithmic trade-offs in the regime that I mentioned. Okay, so delta is fixed, the over-parametrization parameter is fixed, and n becomes large. So let's see what are the consequences of this theorem. The first consequence is the following. So we can obtain trade-offs between adversarial risk and standard risk for this for robust ERM. And here, so these are the curves that you obtain for different values of delta. Remember, delta was the ratio of the number of data points, the number of training data points with respect to the number of parameters. So when data becomes larger and larger, this means that the number of data points becomes larger and larger compared to the number of parameters that our model has. Okay. So as you see, so the black curve at the bottom, the lowest curve, is the fundamental limit, is the optimal trade-off that we can obtain. And as you see, when we increase delta, when we increase the number of data points, the solution of robust ERM would give us the optimal trade-off as we increase the number of data points. So that's the first consequence. Again, using these precise trade-offs that I mentioned, you can also study the effect of over or under parametrization. You can also study the effect of this parameter delta. So in the over parameterized regime, when P is larger than N, so we have a bunch of plots here. So the important thing is the following. When epsilon is small, so I'm plotting the standard risk versus epsilon, and this is the result of the adversarial training methods that we are considering. So when epsilon is small, if you see, the standard risk is it decreases with respect to epsilon. This means that somehow when epsilon is small, when the power of adversary is limited, adversarial training is somehow behaving as a regularization for our standard risk. So it somehow regularizes the model and it decreases the standard risk. However, when epsilon grows, the power of adversary somehow kicks in, and we have all these trade-offs, so you get an increase in the standard risk. The same type of picture also holds in the under-parameterized regime. However, the effect of adversary is much more dominant here. And also we can...
sorry, sorry to interrupt you, but I missed that point now. Right. It seems very interesting and important. So you say when does adversarial training actually improve? Because before you showed us in the fundamental limit, it only hurts, right? In the Gaussian case that you calculated.
Right.
But now why does it, what changed now? This is the algorithmically help?
Exactly. This is the algorithmic effect. Right, very good.
That's very strange. I see. Interesting. Okay.
Yeah.
So to repeat, these Pareto curves are just showing like infinite data. They're not showing they're just saying pick a theta, and I'm going to plot the two numbers, and that gives us these curves.
No, so so theta is the result of the robust training, the solution of the robust.
Or any solution. And I can just plot two numbers. Any theta corresponds to a point on this.
Oh, the Pareto curve, the black curve at the bottom.
Right. Yeah. Of course.
That's the boundary of that region. That's what we can optimally achieve, no matter what your algorithm is. And the other curves that you see in this plot are the result of basically the solutions of robust ERM.
So you get a closed form expression for the solutions of robust ERM in the Gaussian case, right? Which I'm sure is very complicated mathematically to get.
Yes, yeah. There is like 20 pages of derivation. I'll explain a bit about how we can obtain this.
Okay, but let's understand what you were saying now. So you say, okay, somehow you know what the solution will be, and why? Do you have any intuition why adversarial training makes you perform better in this case?
In the algorithmic case, when epsilon is small, that's just a guess. When epsilon is small, it seems to us that adversarial training, the adversary is somehow playing the role of a regularizer for our standard risk. When epsilon is small, when the power is limited, so it basically improves the standard risk. When epsilon becomes larger and larger, somehow the adversary becomes more and more powerful, and then there is no regularization happening. It just hurts the standard risk.
I mean, even with normal regularization, if you make the hyperparameter too important, you're going to hurt yourself, right? So there's some optimal amount of regular. Okay, I see. Very interesting.
Exactly. All right. Okay, so let me quickly say a few words about how we the high-level picture of the proof here. The main point about regression, which basically allows us to derive all these theorems, is that, I mean, in my opinion, of course, is that in regression, the inner maximization could be solved in a closed form manner. Okay, so basically, you can solve the inner maximization and you would obtain a specific loss function for the robust ERM problem that you need to basically study. Okay, so here, if you look, the effect of the norm of the model is inside the loss, inside the quadratic loss. And so since we can explicitly solve the maximization problem, the inner maximization problem, we can basically study this objective. So very quickly, let me just mention the general picture here. So this is the general problem that you want to solve. This is the robust ERM problem that you want to study. So by basically a small change of variables, you can, and looking at the dual of this problem, you can basically write the dual in the following form, where X would be the data matrix, U would be the dual variables, Z would be the difference to the original model, to the ground truth. And the function psi is a function that's basically concave. So let's see, it's convex in Z and concave in U. Okay, so this is just the general formulation that you get for regression for the dual formulation. And then we can use this powerful framework of Gaussian minimax theorems, convex Gaussian minimax theorems, which basically shows that when in the limit of n, you can basically rewrite this objective with respect to some other objective, which is much easier to analyze. This is the Gordon's method that's been used in the non-adversarial setting. However, if you want to use it in the adversarial setting, there are also a few steps. So the framework that doesn't directly apply, there are other steps to do. However, this is the main framework that we are using to analyze these limits. So once we write our objective in the following form, we can basically analyze it using probabilistic tools. So that's the high-level picture. And let me also mention that, so these results were derived for regression. You can also derive similar types of results. The similar effects basically hold in the case of classification when the data comes from a mixture of Gaussians. This is a very recent paper that we are working on with my friend and colleague Edgar Dobrian from Penn, Wharton, as well as my student Alex Roby and David Hahn, all from Penn. So similar type of effects would hold also in terms of classification. All right, so in the remaining 10 minutes or so, I'd like to talk about the second part of this talk, which is about natural out-of-distribution inputs. And this is a joint work with Alex Roby, who's a student at Penn, jointly supervised with me and George Papas also at Penn. And the paper has recently been put on arXiv. Okay, so a very quick recap of what natural variation, this class of transformation was. Basically, the images, the test, the data points that you get during test time in real world or natural environments would basically have a natural distribution shift compared to what you typically train. And these are, you can talk about different types of transformations, such as snow, rain, whatever, dirty camera lenses, different camera poses, and so on. Okay, so there is a very broad class of transformations that you can consider. And in order to make our models robust against this type of natural variation, as I mentioned before, there are two fundamental challenges that we need to address. The first challenge is that we don't really have an explicit analytical model that mathematically models the impact of these natural variation. In other words, we don't have a model that takes as the input an image X and adds a snow to it, or adds a different kind of natural variation. So first, we need to basically try to understand how we can mathematically understand these type of natural variation and how we can model them. And once we have access to a model, the next question is how can we leverage these models in order to devise robust training algorithms? So I'm gonna give you a high-level picture of how we address these two questions through a framework that we call model-based robust training. In order to, so the next few slides will be basically a high-level picture of how we think about modeling and addressing this natural variation, and I'll talk about epsilons and deltas and details later on, again, briefly. So the first challenge was how to model the impact of natural variation. And the way we think about this is simply through something that we call a model of natural variation. So this is just a function, g of x and delta, which takes as input an image x and another input, another argument, which we call the nuisance parameter delta. Delta is typically a very low dimensional parameter, let's say in R2 or R3. And the idea is that given an image x and given a specific value of delta, when you plug this into this model G, you would apply or you would apply a naturally varied version of your image x. And by varying the choice of delta, you would basically obtain different levels of natural variation. So that's how we think about modeling natural variations, right? So by varying the nuisance parameter delta, you can produce images with different levels of natural variation. Of course, I haven't told you how to obtain this model G. That will be done in a few minutes. But what's important is the way we're thinking about this. So there is a nuisance parameter delta, and there is this image X, and there's this function which takes these two as input and gives you different levels of natural variation. So basically, the nuisance parameter delta is encoding the level of natural variation in your image. So let's, for a minute, assume that we have access to this model G. Let's assume that somehow we have obtained this model G. And I want to basically study the geometry of these naturally varied images. So in order to do so, I'll fix the image X and assume that I have access to a model G, this function G. And I want to basically study something that I call learned image manifold. And this is basically the manifold that's obtained by varying the nuisance parameter delta while fixing the point X. Okay, so each point of this manifold would correspond to some specific value of the nuisance parameter. And if you vary the nuisance parameter, you basically sweep this surface or manifold, which is in the same space as the image space. So this is somehow the geometry of natural variation. And this picture should stand in contrast with the epsilon balls, this very simple geometry of epsilon balls, which we considered in the case of adversarial examples. So here the geometry is slightly more complicated. It's not a ball anymore, it's like a surface or manifold in the image space. Now, assuming that, again, you have access to this model G, you can basically leverage the model through this minimax optimization problem in order to do robust training. Okay, and let me explain a bit about this inner maximization problem that you see here. So in the inner maximization problem, basically fixes the data point X and goes over different values of delta and chooses the worst case delta, the worst case nuisance parameter that maximizes the loss. Okay, we will consider different losses, but the basic idea of this inner maximization problem is to find the worst case nuisance parameter that maximizes the loss.
Hamad, delta here is a vector.
Delta is a low dimensional vector. Let's say.
So it's describing the dimension of, I see. So it's something like 50 dimensions or something, I guess.
Yeah, I mean, in our experiments, we use them like 2 dimensions or 3 dimensions. Yes.
Okay, great.
Exactly. 50 also would be a good number. All right. So you go over all the possible values of delta, and you would find basically the worst case nuisance parameter that maximizes loss with respect to the model G and the current weight vector W that you are considering. And then the rest is easy. So you want to find the best choice of parameters that minimizes the expected loss with respect to this worst case nuisance parameter. So this is basically the minimax optimization problem that we need to solve, assuming that we have access to this model G. So now let me say a few words about how do we obtain these models of natural variation. So I'd like to break this class of models into 2 parts, the class of non-models and the class of learned models. The class of non-models would be models that are known a priori, okay? The models that can be obtained using very simple analytical expressions. For example, in the case of norm-bounded perturbations, the model of variation would be just a translation by the amount of noise. So the nuisance parameter would be the noise vector, and you just add it to your data. And the nuisance parameter is within the ball that you're considering out of point. Okay, just a simple translation. In the case of rotation, the model would be equivalent to multiplying the rotation matrix corresponding to the angle that you're considering times your basically data from your image X, and that would rotate your image. Again, a very simple model that you can obtain a priori. You don't really need to learn it, and you have it. And once you have the model, once you have an analytical explanation of the model, you can just use it in this minimax optimization problem to do robust training. Okay, that's basically what's been done right now in the case of adversarial training. Now, the more interesting case, or the more difficult case, is when you don't know the model. Okay, you don't have any analytical expression for the model. And this applies to natural variation. And naturally, the idea would be to learn these models from data. So how do we do that? Let me give you the high-level details of how we can learn these types of models of natural variation. And this is done by using a framework, which is a very famous framework in vision, called image-to-image translation networks. The high-level idea would be the following. You take your input X, and through an encoder, you decompose the input into two parts, the semantic part and the nuisance part. The semantic part would basically capture the main details, the semantic details inside your image, like the details of the street view, the street sign, and so on. And the nuisance part, as we have been explaining up to now, would basically model the effect of natural variation. And so you have the encoder, and then you have the encoder part, which by varying the nuisance parameter would basically model the task of creating different levels of natural variation. So there is this encoding part and the decoding part. If you want to think about this, is like an auto-encoding procedure, which you can train using data in order to find this function g of x and delta. Okay, so in order to train this encoder and decoder, there are a few GANs involved. The details are, let me skip the details right now, and I'll be happy to talk about the details offline, but that's how you basically find this function g of x and delta. Once you find this model, you can basically readily leverage it in this minimax problem. Of course, the minimax problem, solving the minimax problem is itself a challenging task, because there's no convexity or concavity structure that you can exploit, especially if you work with neural nets. So, so we have basically 3 algorithms to solve this minimax problem efficiently. The 3 variants differ in terms of how we solve the inner maximization problem. The outer maximization is typically done by using some like gradient descent procedure like SGD or ATOM. And we are considering alternating minimization and maximization procedures. So for the inner maximization, so we have 3 types of variants. The first variant would be a 0 order optimization method. So at each iteration, when you want to take a few steps for the inner maximization problem, you would just, let's say, pick k points, k random points according to your nuisance parameter, and you would choose the worst case point that maximizes the loss among those points that you have chosen randomly. That's the 0 order kind of optimization algorithm for solving the inner maximization problem. You can also, so we call this a model-based robust training method, MRT. You can also do first order optimizations for solving the inner maximization problem. We call this model-based adversarial training, where you take a few steps along the gradient of the loss to maximize. And also you can talk about model-based data augmentation, where you pick points uniformly at random and you just augment those points in your data set. Okay, so these are 3 variants to efficiently solve this minimax problem. Now, let me quickly also give you some experimental results here. So, well, I mean, there are not many baselines for this problem. As I said, our understanding is quite limited, both in terms of the models and in terms of the algorithms. So I compare to basically a standard empirical risk minimization method and some of the adversarial training methods that are well known in the context of adversarial examples. And our approach, I mean, we have 3 different types of algorithms to basically evaluate the performance of. And we have tested this on a variety of data set. I mean, the paper has like 50 pages of experiments here. I'm going to just pick 2 experiments to basically explain here. So the first experiment is the following. So you use one data set. So this is called the German street signs data set. So this is these are the street signs that are basically taken inside some cities in Germany. We use that data set to learn the model. Okay, so you learn the model offline, right? This model of natural variation, and then you basically try to use the model in real world in your own city. Okay, so then we use the model on a completely different data set. Okay, so you learn the model offline, then you just put everything aside and then use the model later on online. So this is, the model is tested on the Cure TSR dataset, which I think is taken at, the images are taken in the city of Atlanta. So, and this is what you get. Compared to the vanilla methods, compared to the baselines, So the curves at the top are accuracy results for our algorithms, or 3 types of algorithms. And you get around like 20 to 30% of improvement compared to vanilla methods. Okay, and remember, you learn the model, and then you use it. I mean, you don't need to data later on in order to train your classifier. Once you learn the model, you can just use it later on. You can also compose different models of natural variation. So for example, you can learn a model for lighting and for snow, and then you can compose the model. And again, by composing these models, you can also obtain very good, huge, significant improvements compared to the baselines. And finally, I want to also explain some of the results that we have very recently obtained on ImageNet. So what ImageNet dataset is now 10 years old, it's quite famous. There has been some recent effort to add some levels of natural variation to ImageNet. For example, snow, and there is a very wide class of transformations that has been done in this recent paper on the ImageNet dataset. And again, if you use our models, the model-based robust training method on these new data set is called ImageNet C. We see that we get quite significant improvements with respect to the baseline. All right, so this framework basically improves natural robustness against natural out-of-distribution shifts in the input data. Let me try to stop here because I think I've talked too much. Thank you very much, everyone.
Thank you, Hamad. Thank you very much. Really appreciate it. Very nice talk. So is there any question for, there are 2 questions in the chat box that I missed, but maybe we can answer those first and then we can see if there are other questions.
All right, so Ranshi is asking, isn't it expected to have adversarial theta star perform poorly on benign? Because adversarial theta is, no, I mean, it's not intuitive. Consider, okay, let me give you an example. So the question is the following. Isn't this expected that the robustly trained model would perform poorly on benign inputs? Just to explain that this is really not intuitive, let me give you an example in terms of the human vision system. I showed you some adversarial examples that are for us as humans are like indistinguishable. I mean, we can, as humans, at least with respect to these adversarial examples, we can basically have a very good robust accuracy as well as a very good standard accuracy. So there is this human vision system, which is good. You don't pay a price, or maybe the price is really low in terms of robustness, right? So it's not intuitive at all. Another question is...
no, but that's not true, Hamad. That's what your results are basically showing. I mean, of course, it's not true. If you're the more you do, the larger the perturbations, eventually, if you do additive perturbations, it'll confuse our accuracy. It's just that the only perturbations that are compelling to reviewers of papers are ones that are not in the manifold of images, or the ones that we don't see, basically. So.
Excellent.
Yeah, but otherwise, of course, like the more you perturb, of course, you're going to ruin. Eventually, you have to.
Eventually, yeah.
Right. Yeah. Also, if I may add, the discussion I think that you're having is really a discussion about the data, right? So for example, maybe when you're distinguishing cats versus dogs, there is some very subtle pattern in the FAIR that a neural network can see, right? But this super subtle pattern will be very easily removed the moment you're allowed to perturb any at all, right? So in the real question, I think, or one relevant practical question is what Madri and Tsipras and all these guys have been saying, right? There are these things that they call non-robust features, and it's possible that the machines can see them, but humans cannot see them, and they're still helping in the accuracy. And they have made an experimental case that, as far as I understand, I buy, that to some extent this is true. I guess your first paper, and I'm trying to understand the meaning of the first paper, it says that you're analyzing the geometry of balls around points, right, that are all Gaussian, and you're saying that there are some non-robust features, right? And you're measuring exactly how many they are as you change the radius of the ball. Isn't because you show there's always a trade-off. There's never a vertical line in this Pareto, right?
Right, exactly. So, or in other words, what you learn by ERM, exactly as you mentioned, is a set of non-robust features, features, exactly.
I mean, you learn both. You learn. I mean, the classifier will learn to use both the non-robust and the robust. But what you say is, if I eliminate the non-robust features for the Gaussian case, I mean, the biggest assumption obviously is that everything is Gaussian and full dimensional here.
Right.
So one question that I guess I had was, if instead of assuming that the data is fully dimensional, if you assume the data is living in a lower dimensional subspace, even in a, I mean, of course I would want to make it a manifold, but even for a lower dimensional subspace, how does the penalty change in the dimension of the data? Do you see what I'm saying?
Yeah, that's a very good point. And actually we've been thinking about this. Well, no specific results yet, but so the intuition is that if data is in low dimensional manifold, and let's say you train a neural net to, let's say, regress or classify, so this is the manifold. As long as you go outside of the manifold, the neural net is highly non-robust, meaning that the sensitivity will be very high. In other words, if you can easily find adversarial examples by moving outside of the manifold that the data lives in. Now, I think there is a paper by Peter Bartlett's group. It's not about adversarial examples. There's a paper about regression where it talks about exactly this effect, where if your data is in some low dimensional manifold, then and if you train it, let's say an over parameterized model, such as a neural network, or let's say if you increase the number of parameters with respect to the data points in the regression problem, then you can easily, very easily, because your model is only robust when you walk inside the manifold and not outside. You can easily find adversarial examples by just moving a bit outside of this manifold.
Yeah, because the model has never seen anything outside.
Exactly.
Yeah, of course. Okay, yeah, and that's clear.
Exactly. All right, so there was another question in the chat box. Is the robust ERM an upper bound for adversarial risk? No, I mean, in general, this is not true. And as I said, robust ERM is just one way to relax this adversarial risk. There are other papers. There's a very nice paper called the Trades paper. It's known as the Trades paper, which is by a group from Berkeley, Mark Jordan, Jiantao Jiao, El Garoui, and so on. And they consider a different type of robust ERM. I mean, it's not exactly robust ERM, it's a regularized version of robust ERM. And they show that actually that objective is very good in terms of robust training. So it's not an
Thank you.
Right.
Thank you, Ham. I have this question because I noticed you write the delta before the empirical average, the maximum over delta before the empirical average. So I thought you maybe done some reduction over the object.
No. Okay, so that's a good question. You can basically, so I think you are talking about the max being outside of the empirical average.
Yeah.
That doesn't matter. You can, I mean, it's equivalent to bringing the max inside.
Yeah, because you are like a maximum delta I for each component. But at that specific slide, you only write down one delta. So I have this question. But now it's clear. Thank you.
So delta would be the vector. Sorry.
Can I have another quick question?
Sure.
So you write down so you like explicitly solving the inner maximization problem and write down a regularized optimization form. Can I ask if the regularization coefficient epsilon is always positive?
Yes. Okay. So let me just bring it. It's not exactly regular. So there is a solid point here. Let me just bring So if you see here, let me this. So if you see here, the regularization appears inside the loss, inside the quadratic loss. So it's not exactly a regularization if you see it here, right? I mean, it's a strange type of regularization. So the norm is inside the loss. Now, epsilon is always epsilon. Epsilon is the power of adversary, so it's always positive. All right. Did I answer your question?
I'm still a little bit confused. So you mean this epsilon?
No, epsilon is the power of adversary, right? Epsilon is the radius of the ball.
It's a radius of a ball?
Yeah, epsilon, right?
Oh, I see.
is the adversary's like power.
Thank you.
Hi, Dr. Hamad.
Yes, hi, Howard.
Thanks for your talk. And I have basically two questions. The first is on the experimental results. So, like, did you observe the adversarial robustness across like different types of natural corruptions? So, for example, if you do your adversarial training on the snowy images, can the robustness be generalized to other types of corruptions? Like maybe the
very good question. So right now, okay. So what Hauto is saying is this: let's take two different types of natural variation. Let's say contrast as well as the snow. These are two different types. If I train on a snow, do I get robustness in terms of contrast or not? The answer is in general no. So you have to. So the way, and this is, if you look at the slide here, we are talking about composable models. So our idea would be to basically learn a model for each of these type of natural challenges. And then by composing these models, you would be able to find classifiers that are robust against, let's say, two challenges or two or more challenges. That's our solution right now.
I see. Yeah, so and I think you also show the results on ImageNetC. So for that experiments, did you like compose 15 types of corruptions together?
No, okay, very good question. No, not yet. So these are a specific. So the ImageNetC data set has. So for example, it has a subset that's all about a snow, right? And it has another subset that's all about contrast. So we train different models and we train classes, so separate classifiers for each of these plots. Right now, we didn't compose it for ImageNet, so we are basically working on that right now.
I see.
So for each plot, there is a separate classifier that we train.
Okay, I see. I see. Yeah. And I have another question on the technical details. So about how do you get the G model? So I believe you mentioned using image to image.
Right.
The image to image models. Yeah. So I believe in the original image to image translation paper, it's acquiring the Parametrized the training data set. So I'm just wondering whether how do you get a Parametrized the training data set for
very good. So I mean, it's based on this framework, but we train we basically somehow we use this framework, but we used our we basically introduced some new ideas into this framework. So we don't use pairwise basically.
I see.
What we have is that two data sets from two different domains, and this I think there is a follow-up paper on MUnit. If I mean Alex can make
the cyclogram, like the cyclogram.
Sorry?
Is this something similar with the cyclogram?
With what? With SAFE?
With the cyclogram paper,
yeah. So there's I think there is a cyclogram and there is a follow-up paper after that, which basically you can consider two different data sets and basically train a model without considering pairwise data points.
I see.
Right?
And
but what's important here is that, as I said, we changed this framework a little bit, right? So our models are like multimodal, stochastic, and so on, because we want to have different types of natural variation. We want to optimize here. We want to solve the min-max problem.
Yeah. I see. And how did you train the nuisance variable in G? Because I think that should be like something new. Like in the traditional image to image paper, it doesn't have the nuisance variable.
Right. How did we do that?
Yeah. How do you like achieve like by adjusting the nuisance variable and
right.
generalize different?
So well, I mean, this is done. Maybe we can talk about the details offline. But that's actually very. Let me just So this is done by. So when we decompose this into these two parts, so here in the nuisance part, so we would basically inject a noise, a Gaussian noise, instead of considering the nuisance part, right? So what we do is that we introduce a stochasticity into this training procedure, similar to how basically, let's say, GANs are trained, right?
Mhm.
And by just varying this nuisance parameter, so we also have to basically adjust the loss function and so on and so forth. But then we can basically include a level of variability in terms of the nuisance parameter here. That's one of the, maybe you can also look at the paper. I'll be happy to discuss offline. So that's one of the like innovations that we have here.
I see.
Compared to this very interesting framework of image-to-image translation.
I see. Yeah, this is indeed very interesting. Okay, thank you very much.
Yeah, thanks for your very deep questions, actually.
Thank you.
Okay, so if there's no other question, let me just thank you, Hamad, again for giving this talk, and thank you everyone for attending this seminar. It will be it's recorded and it's going to be publicly available on the YouTube channel that we have for our ML seminar series. Thank you all.
Thanks everyone.